the operators in question. And that was proved by Ball, Carlin, and Lieb in '94 for different reasons. So here's how we interpret this in terms of randomness. So the idea is, if you were to look at a state that's being measured, such as the state inside the device when we're carrying out that protocol, you can think of that measurement as taking the midpoint of two operators, the original state and some unitary transformation of that state. And then, if it's the case that that measurement significantly changed the state, so if there's a significant amount of disturbance by the measurement, convexity says that the modified trace has gone down. So what that means is high disturbance implies high randomness. So this is a way of kind of rephrasing the general idea of the uncertainty principle. So the more that the measurement changes the state, the more we must be adding true randomness to the state. So we'll call that the 1 plus epsilon uncertainty principle, and we can bookmark that because we're going to come back to it later. So here's that protocol, and we want to prove security for it. Here's the first attempt. Say that we had an inequality in this form, basically asserting that if the winning probability of a device is high enough, then there's a certain lower bound on the von Neumann entropy of the outputs coming out of the device. So in the most naive setting, this might be a good way to start. Von Neumann entropy measures, in a sense, the number of bits that you can get from a state. So we might attempt to use this to prove security. And it actually does work, but we need to put strong limitations first on the way the device behaves. So this is only step one. If we were willing to assume, if we restrict ourselves for the moment to the independent, identically distributed, non-adversarial case, assume the device is doing the same thing in every round, then this kind of inequality is actually enough to carry out the proof. And that's not hard to show. It's doing the same thing every round. This lower bound here tells us how much you can get if you have multiple copies of that same state. And so the result is you're able to extract pi of c times n extractable bits. So that's all good. And I'm going to call that type of function a simple rate curve. We want to build on that. Now, in the non-IID case, things get a lot harder. We need to allow all sorts of possibilities. The device can remember previous inputs. It can vary its measurements in between rounds. And whatever state it starts with, which could be some mixed state that is entangled with an adversary. And we still need to prove randomness from the perspective of that adversary. One of the neat things to find out is that the same argument, same type of argument works. It just requires modifying the quantities and doing a lot more mathematical work. Von Neumann entropy is a part of a larger family of entropies, the Renyi entropies, and they're just a little more complicated to express. So that would be the Renyi entropy of density operator rho for the parameter epsilon. And the great thing about this is that it behaves a lot like the von Neumann entropy. It is a property that von Neumann doesn't, which is that it actually proves extractable bits in the one-shot case. You can take a single copy of the state rho, and you can necessarily get extractable bits for it. Not so for von Neumann. Natural attempt then would be to take the previous inequality we had and just try to prove some same inequality relating the winning probability to the Renyi entropy. Only problem with that is I don't know of any uniform way to relate these two quantities. The basic problem is that what we have here is a function that is essentially defined in terms of trace. Probabilities correspond to trace. And over here we have a function that is defined in terms of the modified trace. And it's important to realize that even though they may look as if they're close, trace of rho to the 1 plus epsilon and trace of rho, they don't have a uniform relationship. Trace of rho to the 1 plus epsilon could be arbitrarily small in comparison to trace of rho. And since we said this was device independent, we need to allow for that possibility. So the solution to this kind of evolved indirectly in all of our work is that we don't actually work directly with the winning probability, but we work with something similar. Okay, there we go. So this ratio, trace of the winning state to 1 plus epsilon divided by the original state to the 1 plus epsilon, looks very similar to the winning probability, but I just added in 1 plus epsilons to it. And it has a lot of the same properties as the ordinary winning probability.